Welcome to this segment on the Sun-Earth relationship. In this segment, we'll identify the Sun-Earth relationship in space, explain the seasonality with respect to the Sun's orbit, and identify the terms used in defining the Sun's position in the sky. Let's begin looking at the Sun-Earth relationship. We normally think of the Sun moving across the Earth's sky, but we know in reality it's the Earth that moves around the Sun. It's an elliptical orbit around the Sun and more circular than oval. Thinking about our seasons, they originate from this orbit in combination with the Earth's tilt, which is 23.5 degrees in the north-south pole direction. The summer solstice is defined as the time when the northern hemisphere is tilted toward the Sun and ranges from the spring equinox to the fall equinox. Because the northern hemisphere is tilted toward the Sun, it's generally warmer, whereas the southern hemisphere would generally be cooler. The winter solstice is the time when the southern hemisphere is tilted toward the Sun and ranges from the fall equinox to the spring equinox. The southern hemisphere is closer or tipped towards the Sun, and this results in warmer and summer-like weather in the southern hemisphere. So how can we use this to our advantage in planning for solar? Well, we can numerically define the tilt of the Earth using a new term called solar declination. Solar declination, which is also shown by the lowercase Greek letter delta, is defined as the angle between the Sun's direction and the equator, known as the equatorial plane. By using the equatorial plane as a point of reference, the solar declination at the summer solstice in the northern hemisphere is positive 23.5 degrees. In the winter, it's negative 23.5 degrees. In the southern hemisphere, it's exactly the opposite. So at the winter solstice, the declination angle is positive 23.5 degrees, pointed towards the Sun, or tilted towards the Sun. The fall and spring equinoxes are when the angle between the equatorial plane and the Sun is 0 degrees. And it also happens to be when there's exactly 12 hours of sunlight and 12 hours of darkness. Now that we can use the term declination to define the tilt of the Earth at any time of the year, we can also look at the relationship of sunlight on any point on the Earth using latitude and longitude. Latitude and longitude values define location on an Earth's surface using a grid pattern of vertical lines, known as the longitudinal lines, and horizontal lines, known as latitudinal lines. Longitudinal ranges go from positive 180 degrees to negative 180 degrees. Because the Earth rotates in a 24-hour cycle, any given location on the Earth faces the Sun once every 24 hours. And so that longitudinal location really doesn't have much impact on sunlight availability. Latitude, however, is very critical to understanding how much light is available. Latitude tells us the vertical distance from the equator and ranges from positive 90 degrees to the North Pole to negative 90 degrees to the South Pole. This distance has a direct impact on the angle at which sunlight hits every location on an Earth's surface. The next factor we want to think about is how that declination and latitude help to define sunlight levels. We know that based on where we live on the Earth's surface, there's a variation in temperature and sunlight. This is due to that combination of latitude and solar declination. Using some known trigonometry formulas, we can calculate the solar declination for any time of the year. Solving this equation for any numerical date reveals the actual declination on that date for the northern hemisphere and ranges again from positive 23.5 degrees to negative 23.5 degrees. It would be the opposite for the southern hemisphere. Once we solve for the declination or look it up using an online resource, the other factor to consider is elevation angle. This is the angle of the Sun above the horizon for a defined declination. Elevation is 0 degrees at sunrise and at sunset, and reaches its maximum overhead angle at solar noon, which doesn't account for human constructs like daylight savings time or time zone variations. We can calculate the elevation angle by inputting the declination at a specific date and the latitude of interest. The other common solar term is zenith angle, which is just the complement to elevation angle. Zenith angle is the angle between the Sun and 90 degrees perpendicular to the Earth's surface. So the PV field tends to focus on elevation angle instead of zenith angle, but they essentially tell us the same thing. The final angle that we need to be concerned with is azimuth. So while the sun goes from low angles to high angles during the day, defined by elevation, and during the year, defined by declination, it also travels from east to west over the course of the day. That angle is defined as azimuth angle, which is a compass-based direction of incoming sunlight. North is defined as 0 degrees, south is defined as 180 degrees. During the day, the sun rises in the east, 90 degrees, and sets in the west, 270 degrees. In the northern hemisphere, 180 degrees is considered due south, and the sun reaches that point at solar noon. These terms may be easier to visualize by looking at paths of the sun for the northern hemisphere. The sun always rises from the east and sets in the west and reaches its maximum at noon on that day. On the summer solstice in the northern hemisphere, the sun is at its highest angle, and it's at its lowest in the sky in the winter solstice. It's at mid-range at the equinoxes for fall and spring, giving us variations in seasons based upon the Earth being tilted toward or away from the sun. So what does this mean for solar? Well, we can now think about where we live and then how to plan for solar energy. For example, if you live near the equator, the sun is generally going to be overhead all times of the year. However, if we live high in the northern hemisphere, the sun's angle is very low and there's not much overhead sunlight, especially during the winter season. So if we want to plan for photovoltaic installation, we want to have an idea of both where we're located on the Earth's surface in terms of latitude, as well as how the seasons might impact solar availability. You should now be able to identify the Sun-Earth relationship and how the Earth rotates and its tilt explains the seasons and available sunlight. You should also be able to identify the solar positions using declination, solar elevation, zenith angle, and azimuth angle. In the next segment, we'll explore how sunlight reaches the Earth's surface and how to measure those sunlight levels.